Okay. So, yeah, can someone just list out what all we learned last class? Just type the topics that we learned in the last class, just to like get an idea of if people are following. Anyone? Fine. So, last class we learned, I think, about combination of reactors. And then we learned about recycled reactors. So these were the two main topics from last class. So today, what we'll do is we'll learn some things about reactors um, in in series, and we'll also learn some more details about multiple reactions. Okay, I think we learned this reactor in series, right? I think we learned these three in the last class. So basically today we'll learn a few things about multiple reactions. Okay. So let us start with parallel reactions. So just simple example, A gives R and A gives S. And let's say K1 is the rate constant, K2 is the rate constant. So we learned about the selectivity and yield of these products, right? So let's say selectivity of R will basically be rate of reaction of R by rate of reaction of S. And if you want to find yield of R, it will basically be, you know, rate of reaction of R by rate of reaction of A. So I think we have already looked upon how we arrived at these, formulas, because selectivity is basically the rate of desired product by rate of undesired product, and yield is the rate of desired product by total reaction rate. Right. Now, let's do something. So let's take the selectivity for this. So selectivity, we have it as RR by RS. So what is the rate of reaction of R? That is K1 Ca raised to N. Let us say this is an nth order reaction and this is an mth order reaction. Okay, so just for namesake. So RR will be K1 Ca raised to N and R2 will be K2 or RS will be K2 Ca raised to M. So this will be K1 by K2 Ca raised to N minus M. Okay. Now by Arrhenius we can write K as K0 e raised to minus E by RT, right? So let's say K1 will be K10 e raised to minus E1 by RT, and K2 will be K20 e raised to minus E2 by RT. So now if you substitute these equations for K1 and K2, you know we'll get something like selectivity is equal to K10 by K20 e raised to minus E1 by RT by e raised to minus E2 by RT into Ca raised to N minus M. And we can simplify this. Just take the denominator exponential to the numerator. So we'll get, let us take this as some kind of constant, let's say a. So a into e raised to minus of e1 minus e2 by rt ca raised to n minus m. So this will be the equation for selectivity of one product from a parallel reaction, right? Okay. So now let us uh, let us do something. Now, if we want, now let's say we want to have the maximum selectivity. Okay. So what this equation helps us to do is we can maximize selectivity by, increasing the concentration, or, if by looking at the activation energy of these two reactions. So I'll explain, I'll show it to you guys. Wait. It's equal to a e raised to minus of e1 minus e2 by rt into ca raised to n minus m. Okay, so this is our equation for selectivity, right? Now if we want to increase selectivity, how we can modify in terms of the concentration? So concentration is basically, ca, the concentration term is ca raised to n minus m, right? So now if, let's say, order n is greater than order m, okay, in that case this ca raised to n minus m will be basically something like, ca raised to a positive integer, right? So in this case, so if the order of n is greater than order of m, if we increase the concentration, so if we increase this ca, this whole term will go up also, right? So if ca increases, ca raised to n minus m also increases, and this means selectivity also increases for this case if n is greater than m. But let's say if it is, n is less than m, in that case ca raised to n minus m will be basically ca raised to a negative number, because m is greater than n. If this is the case, then it is better to increase the selectivity, we decrease the concentration of A. So if Ca decreases, Ca raised to n minus m will increase, and selectivity will also increase, right? Now this is how you can manipulate the selectivity with respect to, changing the concentration. Now we can do the same by changing the temperature as well, because here E1 and E2, so activation energy for a given reaction will always remain constant, right? So it doesn't change, so we can't change the activation energy as such. So what we can do is we can change the temperature based on the activation energies. So let's take, case 1, n is greater than m. Oh sorry, we have already looked at this, right? Oh yeah, and one more case, n is equal to m, right? So if in this case Ca raised to n minus m will be Ca raised to 0 basically. So that means this selectivity will be independent of the concentration. Okay, so these are the two cases. So this is case 1, n is greater than m. This is case 2, m is greater than n, and this is case 3 where n and m are equal. So this is how we can manipulate our selectivity with respect to the concentration of the reactant. Now we were looking into how we can manipulate it based on the temperature and activation energies. So let's take case 1, E1 greater than E2. So that means, activation energy of experiment 1 or reaction 1 is greater than activation energy of reaction 2. Okay. So in this case, this S is equal to A e raised to minus E1 minus E2 by RT Ca raised to n minus m. So here, if E1 is greater than E2, that means this term will as a whole become negative, right? So it will become something like EA e raised to a negative term by RT Ca raised to n minus m, right? So here, if we want to increase the selectivity, what we have to do is we have to increase okay, not increase it basically. I'll come to that point. Yeah. So here, if we want this selectivity to increase, this e raised to minus negative term by RT term should also increase, right? Because everything else is, we are not considering it. So for this term to increase, we have to increase the value of the temperature, because there is a negative sign here. So if we increase the temperature, that means the denominator of the exponential will increase, or the overall value of the exponent will become less and less negative as we increase the temperature. So I'll show you one example. So let's take this, E1 minus E2 by RT. So let's take two cases. So let's say, the numerator is minus 100 by R, and now T. Now let's say we have the case 1 as, let's say 300 Kelvin. So this is basically, minus 1 by 3R, right? Now in another case, if we increase the temperature to, let's say 3000, in this case it will be minus 1 by 30R, right? So out of these two, we can definitely see that, the value of this is more. That means this is more negative compared to this, right? So that is why if we increase the temperature, the overall value or the overall negativity of this exponential will decrease, and it will lead to an increase in the value of this whole exponential term. And so, if we increase the temperature, the selectivity will also increase. So this is one case where E1 is greater than E2. Now if we go to case 2, E1 less than E2. In this case, again, the exponential term is basically, E1 minus E2 by RT minus, right? So here, since E1 is less than E2, that means E1 minus E2 will be negative, or minus of E1 minus E2 will be positive. So this whole exponential term is basically a positive term by RT. Okay, so now it is the reverse of the previous case. So if we want to increase the selectivity, we need to increase this exponential term, and to increase this exponential term, we have to decrease the temperature, right? And if we increase the if we decrease the temperature, the selectivity will increase in this case, because as the temperature decreases, the exponent term will also gain more value because the numerator is positive here. So this is the case 2 where E1 is less than E2. Then the final case K3 where E1 is equal to E2. In that case, E1 minus E2 will be 0, and this exponential term will be exponent of 0, which is 1. That means the reactions, the parallel reactions where the activation energies for the two parallel reactions are same, it these reactions, the selectivity of these reactions will be independent of temperature. Okay, so this is case 3 for this parallel reaction and how we can increase the selectivity, right? Okay. um, we can even apply this for more complex reactions, parallel reactions. So let's say we can have something like A plus B gives R and A plus B gives S. So here the rate of reaction of R will be K1 Ca raised to N or N1 Cb raised to M1, and here Rs will be K2 Ca raised to N2 Cb raised to M2. So if we want to find the selectivity of, let's say, Sr, it will be Rr by Rs, and that will be K1 CoA1 raised to N1 Cb1 raised to M1 by K2 Ca raised to N2 Cb by Cb raised to M2. Sorry, right? 1 second. Right. So we can rewrite this as selectivity is equal to K1 by K2 Ca raised to N1 minus M1, N1 minus N2, right? Yeah. N1 minus N2 Cb raised to M1 minus M2. And we can again have a lot of different cases, like let's say one case will be N1 greater than N2, but M1 will be less than M2. So based on this, how can we keep the concentrations, how can we introduce the concentration such that we can maximize the selectivity? So let us just look into this case. So let's say N1 is greater than N2. So that means this Ca raised to N1 minus N2 will be positive. So it is better to keep Ca high or increase the Ca, right? And since M1 is less than M2, the Cb raised to M1 minus M2 will be negative. So to increase the overall value of this Cb raised to M1 minus M2, we have to keep the Cb uh, in low concentrations. So this is how we can see how we can increase or decrease the concentrations of the reactants in order to maximize our selectivity, right? So we can even do this for the activation energies as well. The it'll definitely be more complex compared to the previous case where it is just A gives R and A gives S, but we can extend that to such reactions as well. So this is what I wanted to tell you guys regarding the multiple reactions. So this is about parallel reactions. Okay. Any doubts so far? Okay. And of course, you can have much more cases like this, n1 less than n2, m1 less than m2, or n1 greater than n2, m1 also greater than m2, or both are equal, n1 equal to n2, m1 greater than m2, then n1 greater than n2, m1 equal to m2. So you can have like variety of cases like this, and based on the value of n1 and n2 and m1 and m2, you can decide whether you want to keep the concentration of this particular reactant as high or low. Right? Fine. So that is about it for parallel reactions. Now let us look about something in series reactions. Okay. So now let us say we have a reaction like this. A gives R gives S, and we have the rate constants as K1 and K2. Right. Now for series reactions, we have learned one term as T optimum. Right. This T optimum is nothing but the time at which the concentration of the intermediate product is maximum. So this is T optimum. So this is the concentration of the intermediate product CR, this is CS, and this is CA. Right? I hope you guys remember this. So this is T optimum, and at T optimum CR will be CR max, and since concentration of R is maximum and it is at T optimum, the rate of R will be 0 at T optimum. Okay, and we have also learned equations for T optimum. So T optimum is equal to ln K2 by K1 by K2 minus K1, right? And we also had an equation for CR max as CA0 into K1 by K2 the whole raised to K2 by K2 minus K1. I hope you guys are able to recollect these concepts for T optimum and CR max. Okay. Um, you guys, I hope you guys remember these equations and remember how we derived these equations. Anyways, so these two equations that we learned so far for T optimum and CR max, these can be used only for PFR. Okay, PFR, and I think we can even extend it to batch reactors. But these equations are not usable in CSTR. So for CSTR, we have a different set of equations. Okay, so we can write series reaction in CSTR. Okay, so the same reaction, A gives R gives S, and K1 K2. Okay, now we are not going to be like deriving the whole thing again, but I'll just give you the formulas of how we can arrive at the T optimum for series reaction. And here T optimum will can be represented as tau optimum. Okay, so tau optimum for CSTR will be 1 by root of K1 K2. Okay, and CR max will be equal to CA0 by K2 by K1 the whole raised to 1 by 2 plus 1 the whole square. Okay, so this is the T optimum or tau optimum and CR max for series reactions in CSTR, right? And if we want to see how it is differing, so we can show it using a plot like this. So let us say this is CR and this is tau, right? So this will be the concentration profile of CR in PFR. Let us say if you want to do the same for CSTR, it will be like this. So this will be CR max in, oh sorry, this is CR in CSTR. So this will be the CR max for CSTR and this will be the CR max for PFR. So you can see, there is a difference like this much in the maximum concentration of R with respect to PFR and CSTR. Because we have learned, for a positive order reaction, PFR will always give you a better conversion compared to CSTR. So you can see that difference in the maximum concentrations for PFR and CSTR with this graphical plot as well. And the optimum time also. Where is it? Okay. So the optimum time also. Okay. The power is gone here. Okay, fine. We'll continue anyways. Let's see. Okay, so for optimum time also, we can see, this is tau optimum for, yeah, tau optimum for CSTR, and this is the tau optimum for PFR, right? Because we have also learned that for a given conversion, the space time required in a PFR will be lesser compared to a CSTR for a positive order reaction. So these are just some graphical representations of these things. So is this clear? Okay, fine. So yeah. Okay, so it's 10:40. Fine. Let's move on to some questions. There's a power cut here, so just bear with me. I'm not able to turn on the video. Anyway, so let's move on to the questions. So just read through this question. We'll look into it in a minute. Okay. Fine. Let's see how we can solve this question. Okay. Right. So This is a question from GATE 2019 Chemical Engineering, question number 46. A first order irreversible liquid phase reaction A gives B with reaction rate constant K is equal to 0.1 minute inverse is carried out under isothermal steady state conditions in the following reactor arrangement comprising an ideal continuous stir tank reactor and two ideal plug flow reactors. From the information in the figure, the volume of CSTR in liters is dash rounded off to the nearest integer. So this is the figure given. So we can see that there is a stream of Ca0 or Ca which is divided into two streams, one going into CSTR and the other going into a series of PFRs, and we are asked to find the volume of the CSTR in liters. So this is a question from combination of reactors, and we can get the reference NPTEL series in module 1 lecture 27 PFR and MFR in series chemical reaction engineering 1 homogeneous reactors by Professor K Krishnaya, Department of Chemical Engineering, IIT Madras. Okay, so now here there are a few concepts that we need to apply. So in the figure we can see that one of the streams is a series of PFR, and the concept is that for PFR in series, let's say there is a PFR V1 connected to a PFR in series with the volume V2, then we can consider this as a single PFR V1 plus V2. Yeah, so essentially if we have two PFRs in series, we can consider that as a single PFR with the volume as the sum of the volumes of the two PFRs. So that is what we'll be using here to solve this question. Now the unknown here is basically the flow rate. So here the total flow rate, they have given the total flow rate nu 0 as 100 liter per minute. Now this total flow rate gets divided into two. Let's say this is nu CSTR and this is nu PFR. We are not sure how the flow rate is getting distributed into these two streams. So that is what we need to first find here. Fine. So nu 0 will be nu PFR plus nu CSTR. Alright. So now let us consider the case of PFR in series. So we have two PFRs like this, and it is given that the initial concentration Ca0 is 2, it is 1, and the flow rate is mu PFR. Now the volume of the first PFR is 40 and the second PFR is 60 liters. And let's say Ca is the final concentration here. Now the Ca is given as 0.5. We can redraw this like this. So this will be Ca0, which is 1, and the flow rate mu PFR, and the volume will be 40 plus 60, and will be 100 liter volume, and the final concentration Ca as 0.5. Now if we write the design equation for PFR, it will be tau, which is V by nu, and that is equal to integral of minus dCA by minus RA from Ca0 to Ca. Let us substitute all our values here. So we have as 100 liters by new PFR, that will be equal to integral of minus dCA by RA, and the reaction rate here is, first order. So the reaction here is A gives B, and the reaction rate minus RA will be KCA in both the cases. So we'll write that here, KCA from CA0, that is 1, and CA, that is 0.5. And also K is also given as 0.1 minute inverse. So now we can integrate this and substitute the values of K also, and we can find the value of the flow rate of the PFR, that is new PFR. So 100 by new PFR will be equal to 1 by 0.1, and that is 1 by K, which is 1 by 0.1, and integral of dCA by CA will be ln CA minus of ln CA from the limits 1 to 0.5. So 100 by new PFR will be 1 by 0.1, that is 10, into ln 1 by 0.5. So new PFR will be 100 by 10 into ln 1 by 0.5. So this is basically, if we cancel this 10 and 100, it is 10 by ln 2. So if we do the mathematical operation here, we'll get new PFR as 14.43 liter per minute. So what this means is basically, this new PFR 14.43 will be the value of the flow rate that is going to the series of the PFRs, right? So we had the equation for the total flow rate. Nu 0 is equal to nu PFR plus nu CSTR, and this nu 0, the new total was 100, and that is equal to nu PFR, that is 14.43 plus nu CSTR. So from this we can find the amount of flow rate that is going to the CSTR. So nu CSTR will be 100 minus 14.43, and that will be 85.57 liter per minute. Alright, now let us move on to the CSTR. What we need to find here is the volume of the CSTR. We need to find the volume of CSTR, and for that we will directly use the design equation for CSTR. So the design equation is tau CSTR, which will be V by nu CSTR, and that will be equal to CA0 minus CA by minus RA. So now what we have to do is we have to substitute all the values that we have. So we have the value for new CSTR, we have the value for CA0, we have the value for CA, and this RA is basically KCA, and we have the value for K as well as CA. Now we can substitute all these values and find the volume of the CSTR. So V by new CSTR is equal to Ca0 minus Ca by Kca. So V by new CSTR, that is 85.57, that is equal to Ca0, that is 1, minus Ca, that is 0.5, by zero point 0.1 into 0.5. So if we do the right hand side, it will be 0.5 by 0.05. So, V, the volume of CSTR will be equal to 85.57 into zero point 0.5 by 0.05. So this is basically 1 by 10. Sorry, that is 10 by 1. So V CSTR will be 85.57 into 10, and it will be 8855.7 liters. And since we are asked to round it off to the next integer, the VCSTR will be approximately 856 liters. The correct answer may vary between 850 to 860 liters. So the volume of PFR CSTR in this question, rounded off to the next integer, will be 856 liters. Okay. So basically what we did here, I hope you guys are able to follow. So basically what we did here is we had one unknown here, and that is how the flow rate was distributed between the streams that went to CSTR and the other stream that went to the series of PFR. So to find that, we use the design equation of PFR, and we also use the concept that two PFRs in series can be equivalent to a one PFR which has the volume as the sum of the two PFR's volume. So we used these concepts and we applied the design equation of the PFR. We found out the flow rate that went into the system of PFRs. Then using this flow rate balance, we found the flow rate that went into the CSTR, and then we just directly used the design equation of the CSTR and finally found out the volume of CSTR using the design equation. And the volume to the nearest integer came to be 856 liters. Is this okay? Okay. So we'll look into one more question. So just read through this question. We'll see how we can proceed with this. Okay. So this is a question from GATE 2019 from Chemical Engineering, question number 47. The elementary liquid phase irreversible reactions A giving B giving C takes place in an isothermal ideal continuous stir tank reactor. Pure A is fed to the reactor at a concentration of 2 mole per liter. For the residence time that maximizes the exit concentration of B, the percentage yield of B defined as the net formation rate of B by consumption rate of A into 100 is dash rounded off to the nearest integer. So this is a question from multiple reactions part from chemical reaction engineering, and the reference NPTEL series can be found in module 1 lecture 33. multiple reactions part 2, chemical reaction engineering 1, homogeneous reactors by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So here we have been given an elementary series reaction. A gives B giving C, and it happens in a CSTR. So now let us see how we can represent this. So we have a CSTR, and inside the CSTR pure A is fed with the initial concentration of Ca0, and this is given as 2 liter mole per liter, and then we'll have the final product stream like this. And the thing to note here is that the reaction here is A giving B giving C. So the final concentration will have concentration of A, concentration of B, as well as concentration of C. Okay. So we have the reaction rate constants as well as 0.4 and 0.1. Now in a series reaction, for the rate of reaction of A, we can have the equation as K1Ca, because these are elementary reactions. So these are first order series reactions, and we can write the rate of consumption of A as minus Ra, that is equal to K1Ca. Now similarly, if we write the rate of reaction of B, it will be K1Ca minus K2Cb. And the rate of formation of C will be K2Cb. Right. So now they have said that the time or the space time or the residence time is such that it has the maximum conversion of B. This basically means this space time that they have mentioned has the maximum conversion of the intermediate product in the series reaction. So by concept, this means they are referring to the optimum time. So in a series reaction, the optimum time, we have seen the graphics here. So if this is the concentration of the intermediate product, optimum time is the time at which the concentration of this Cb will be maximum. Okay. Now for series reaction in CSTR, the optimum time tau optimum will be given as 1 by root of K1 and K2, where K1 and K2 are the reaction rate constants of the different series reactions that is happening in the system. So if we substitute the K1 and K2 here, we can find tau optimum as 1 by root of 0.4 into 0.1, and that will be 1 by root of 0.04, or it is 1 by 0.2, and that will be 5 minutes. So tau optimum, or the space time that we need to find here to proceed with the question, is tau optimum, and that is 5 minutes. Okay, so now what we can do is we can write the design equations for our system. So here what we need to find here is the yield of B. Yield of the intermediate product B, and that has been given as RB by minus RA. Now if we expand this yield of B will be RB and that is K1Ca minus K2Cb by minus Ra, that is K1Ca. So here the known values are the reactant rate constants K1, K2 and the denominator also K1. So to find the yield of the product B, we need to find the concentrations Ca and Cb. So to find the concentration Ca and Cb, we'll resort to the design equation of the CSTR system. So now let us first write the design equation of the CSTR in terms of reactant A, and that will be tau, which is V by nu, will be equal to Ca0 minus Ca by minus Ra. So here in this design equation, we have found that tau is basically the tau optimum, and that is 5 minutes. And we also have the initial concentration Ca0, and so the only unknown here is the final concentration Ca. So using this design equation, we can find the concentration of Ca. So substituting the values, tau will be 5 minutes, and that is equal to Ca0. Ca0 is given as 2 minus Ca by minus Ra. So this minus Ra will be K1 Ca, and K1 is given as 0.4. So 0.4 Ca. Now if we solve this, we'll get 2 Ca is equal to 2 minus Ca, or basically Ca will be 2 by 3, and that will be 0.667 mole per liter. So this is the value for Ca. Now the same thing we can do using the design equation of CSTR in terms of the product or the intermediate product B. So design equation of CSTR in terms of B. This one we can write it as tau is equal to Cb minus Cb0 by Rb. Now the thing to note here is that in the question they have mentioned that the feed is pure A. So that means this Cb0 will be 0. So tau will be basically Cb by Rb, and Rb we have written it as K1 Ca minus K2 Cb. So now what we have to do is substitute the values here as well in this design equation. So the tau here is tau optimum, that is 5 minutes. Cb is the unknown. We have the values for K1, Ca and K2. So substitute these values and we can find the value for Cb. So substituting, tau, which is 5, is equal to Cb by K1, and that is 0.4 into Ca, that was 0.667, plus K2, which was 0.1 into Cb. So now if we solve this equation to find the unknown Cb, what we can do is 5 is equal to Cb by 0.2667, sorry, it's a minus here, minus 0.1 Cb. So Cb will be 0.889 mole per liter. Okay, so now we have the concentration of Cb, and Ca also we found out as 0.667 mole per liter. So now we can substitute these values in the formula for yield of B and we can find the required answer. So yield of B was minus RB by minus RA. So that is K1CA minus K2CB by K1CA. So YB is K1CA minus K2CB by K1CA. Now substitute all the known values here. It will be 0.4 into 0.667 minus 0.1 into 0.889 by K1, that is 0.4 into 0.667, and this is into 100. So if we solve this and do the mathematical operations, we will get the final yield as YB is equal to 66.67%. This is the yield of the product B. So the right answer here is 66.67%. And since they have asked us to write it in the nearest integer, it is 67%. Okay, is this clear? So basically what we did is in this equation, um, to find the yield of the product B, this was the formula K1CA minus K2CB by K1CA. CA, CB are unknown and we need to use the design equation of CSTR in terms of reactant A and product B to find CA and CB. But in order to use the design equation, we need the value of tau. And for that only, they have given in the question that tau is the time at which the CB is maximum. So that is the concept of the optimum time in series reaction. So we can first find tau using the optimum time formula as tau optimum is equal to 1 by root of K1 K2, and we can find the tau optimum here as 5 minutes. Now we have all the tools required to apply the design equations to find the concentration of A Ca and concentration of B Cv. So we'll do that only. We'll do the design equation of CSTR in terms of A and B using the tau that we just found out, and we'll find the concentrations of A and B, which are Ca and Cb. Once we found the concentration of Ca and Cb, all we have to do is just substitute them in the yield equation and finally find the yield using this same equation, and we'll get the yield as 67%. Okay. Any doubts? Is this clear? Can anyone respond? Should I explain this again, or like is this fine? Okay. Fine then. We'll stop here for today. So if everything is clear, I guess we'll stop the class for now. We'll do a few more questions with regards to this reactors and reactions. Maybe one more class of this, and hopefully by after the next class we can start with the non-ideal reactors, which is basically the start of chemical reaction engineering 2. So we so far we have looked mostly into CRE 1 only. So we'll try to start CRE 2 maybe in 1 or 2 classes, and after non-ideal reactors we can look into some parts of catalysis as well. So yeah, let's see how things goes. And yeah, that's it for today. Thank you for joining, and I'll see you guys next Monday.